I'm Lowell Winger with IDT, and my topic is optimizing ABR encode, compute, and control for performance and quality. So as you may be aware, ABR encode has unique properties that you can leverage for optimization beyond what you can do with traditional linear broadcast encoders, which is actually my background. But these are the new things that we're doing, so I hope you I have a lot that I want to cover here today. But first of all, what I'll start off with is talking about the background, which is the base encoder that we're working from, and its strengths. So we've taken a premium broadcast encoder, broadly deployed, and it's now an FFmpeg streaming plugin. And that's so it's available in the cloud and on premise, both on Xilinx programmable devices, FPGAs, so the VU9P, and on Intel processors, on Xeon processors. And today I'll emphasize the scalable processors because we have some nice gains specific to those. But it's available across the board on available generations of Xeons, V3, V4, Broadwell, Haswell. So really two topics I'm going to talk about. As I mentioned, computational gains is the bulk of my talk. And for that, I'm going to talk about deep profile reuse. So what I mean by deep profile reuse is the output ladder, the outputs from your encoder for ABR streaming. Some people, you may have heard, do reuse between the computations needed to produce those outputs. And some people will start in a bottoms-up fashion from the smallest output and reuse computations towards the largest output. Other people will start from the top down. What we've done here is we do both, because by doing both, you can get both performance gains and quality gains. You can save compute, and you can also improve your video quality at the same time. So I'll give one example of bottoms-up, which is a hierarchical motion estimation search, which is the gold standard for video compression in terms of quality, and what reuse we do there to get gains. I'll also cover a tops-down example, which is our output encoding order and our complexity analysis. In encoders, you do a lot of analysis up front. You want to know where the areas of complex texture are, so you know where to put bits. You want to know where the areas of complex motion are, so you know where to put bits, and where to save bits, so that you achieve the best visual quality. So that's, and then finally, on the topic of computational gains, the final piece of the puzzle is we have a fast computational control system that sits on top of everything and ties together the bottoms up and tops down to ensure that cycles are never wasted on the platform. So this differs from what you might be used to, a kind of fixed quality preset. This has hundreds of quality presets and dynamically moves between them. So it's optional, but it's a nice gain. It's some nice gains, so I want to introduce it to you. Then I'll quickly go through a small section, which is control-related gains. So this is an immediate control per scene, per scene encoding. So that's an intelligent, fast, very low overhead, latency-free, so overlapped with the encoder so that it can be offered for live at low latency. ABR encoding with per-title quality, cost-effectively brought to live file in short form. And the key thing there is the immediate control adaptive resolution. So because it's overlapped with the encoder and tied into the encoder, we have immediate control. So we're able to do the optimal choice in terms of what to use for encoding on an output profile to get the best video quality without guessing using some estimation or some prediction. Rather, we know what the right choice is, okay? And it's tied in with our rate control, both CBR and CRF. So that's the bulk of the presentation. So first, the base encoder, our strengths on quality and performance. It's been brought to an FFmpeg streaming framework from a very broadly deployed premium broadcast encoder. The quality and performance methods that I'm going to talk about apply to all the codecs and across all the platforms that we offer it, the ones that I mentioned previously. The key value is that we offer twice the FFmpeg transcode channels with better than X264, particularly temporal quality, which is not normally captured by a lot of metrics, but is key for broadcast quality. Offered on FPGAs, x86s, on-premise cloud, and value proposition of 15% better quality, so noticeably better. You can see 15%. noticeably better quality, and 50% less infrastructure cost. So that's the base, available, as I mentioned, on FPGA, the Xilinx VU9P, which you see here, on-prem PCIe card, 40 watts for 8 HD transcodes. So 5 watts per HD transcode at a broadcast quality. This is the base, remember, that I'm talking about right here. So the other topics that I'm going to discuss later are the gains on top of this base for ABR. It's a portable IP using Xilinx SDXL, available on Huawei FP1 Cloud, Alibaba F3 Cloud, AWS EC2 F1 Cloud, Xilinx VCU1525 on-premise card, and this Advantech Vega 4000 card that you see here. Last slide on the base encoder strengths. Just the Xeon x86 cloud and on solution. What we did is, just to let you know what we can do on a Skylake, a 6148 SKU, that's a Gold processor, a very cost-effective processor, very similar compute to the previous, and cost to the previous generation Broadwell processor, 2697, which is broadly deployed in data centers. Maybe within 10% of compute in terms of core times gigahertz total compute available. When we benchmarked it for equal quality with full HD streams, 1080p by 1920 p60 in a live use case across a number of common contents, you can see that the gains of the Skylake part over the Broadwell part were more typically 30% and fairly stable. So that translates to 30 live HD channels on that Skylake part. So those are, that's something that you're not going to get from an open source solution that they leverage the new generations of Xeon processors. So to get further gains on top of the base code. So getting into the bulk of the deep topic today, the deep profile reuse and the computational gains that can be gained for ABR, I'm going to cover a hierarchically pruned full search motion estimation. So the key here is the pruning. So if you look at the flow chart, we're going to start with a large number of reference frames. So that lets you get a good quality. If you have a large number of reference frames, you're talking about being able to compensate uncovered, covered areas well, finding objects that have moved on and off screen. You can lower your bits, increase your quality. Hierarchical motion search is not new. As I mentioned, it's a gold standard for video quality. But what is new here is we start the motion search on the small profile output, where compute requirements are small. And we use very large blocks that cover, in terms of they're covering a large portion of the scene. So at a small compute, we winnow down the reference frames that we're going to search later as we cycle through the hierarchical stages of the motion search, so that in specific areas of the picture, we're only searching the best reference frames, the ones that really need to be there with a higher number of cycles. So I'm going to show you graphically what that means. But this is basically the flow. We move from very small, this is the bottoms up reuse to save compute and increase video quality. So here it is graphically, and I have a number of slides here. So you can see the red lines. At the bottom is our current picture. So I've limited it to 4 reference pictures here. In practice, we would start with a much larger set. In this first stage, we're going to winnow it down to what the decoder can handle. So what's compliant with the standard, which depends on your profile and level. So first of all, we're going to search all of those large areas in the small resolution outputs, so the bottom rung of your ladder, using very little compute. And for each of these 6 blocks, those large blocks in the current picture, which is at the bottom, we're going to see which ones of those we want to keep for later stages. So first stage is search on the mega blocks. Second stage is sort and prune. So picture B, the second from the left, we've grayed that out because that's not a good reference. And we need to drop complete pictures at this point to get something that the decoder can handle. So we're going to drop some complete pictures. We mark the B picture as red just to give you an idea of what these slides are representing. We're going to prune out the B reference picture from our list of ones that we're going to use for temporal reference. Okay, second step, we move to a smaller block size. We move up the rung of the ladder. Here, the remaining 3 pictures, picture A, C, and D, which is probably actually 6 to 8 pictures in practice at this point that a decoder can really handle. We're going to go through the smaller blocks on the current picture because we've moved up the rung of the ladder. And we're going to reuse this compute for each of the rungs above as we cycle through. And here, the list is starting to change now in the next step. So first step here is search again at this resolution and get our scores. Second step is prune, and you can see the red letters that we're dropping on those blocks are differing per area of the picture. So we're reducing our reference pictures to the ones that matter on particular areas of the picture, because there's certain objects moving off the screen and on the screen, so only certain reference pictures are good for certain areas. Okay, so that's an example of our bottoms-up reuse. And this is on the order of 30% gains in terms of what you can get on top of not doing reuse, in terms of number of channels that you can put on a box. But we're using a gold standard for motion search quality. Okay, now I'm going to cover a tops-down example. So again, just like I had in the last one, I have one complex slide up front with a flowchart, and then I have some simpler ones to explain it. So here for tops-down, we have on the left, we have our output ladder from large at the top down to small at the bottom. And we're going to put it through a configuration manager, which is going to scan those outputs and figure out what can we reuse in terms of these complexities that I need for analyzing the video, the motion complexity, the texture complexity. What can I reuse between those outputs in that analysis stage of the encoder, which comes before the look-ahead buffer for your rate control? So if we start at the very top of the content analyzer, the center block in this slide, we're going to do most of the computation here because it's tops down, and we want to keep very fine granularity information for this type of information because it really impacts your picture quality. And when we reuse that for the bottom rungs, those bottom rungs are actually going to improve in quality even though we're eliminating the compute for those rungs because they're getting better quality, higher granularity information on those lower rungs. So that's what I'm talking about in terms of deep profile reuse. So the second rung down can fully reuse the top rung because the only thing different between those two is the frame rate. All compute reused. Third rung down, we can reuse all the results, but we have to scale the results because it's a slightly different resolution. Third rung down is actually a factor of 2 of one of the top rungs, so we can just decimate. We don't have to scale the results. We just pick them. Very low complexity, right? So this is the approach that we use to save compute and improve quality in a tops-down fashion. So here's a more graphical look at it. Again, I mentioned 30% more channels and higher quality through ABR reuse. So this is looking at, now you notice there's one column here of compute. These are the compute columns are spatial analysis, what I talked about, decimating pictures for the resolutions, encoding order decisions, motion estimations, right? We're going to save these compute stages at each of the rungs, each of the ladder outputs, from the top profile down to the bottom profile. Some are completely reused, as you can see from the legend on the right. Some are reused with scaling. Some are reused through simple decimation. The second column, there's a lot of reuse going on there. And where is that reuse coming from? It's actually coming from outside the encoder. It's coming from the scaler. So we've integrated our reuse of the encoder with the scaler. That's not really the topic of today. I was going to just talk about the encoder. But there is more reuse going on here than just the encoder reuse. So the final piece of the puzzle, we have our tops-down reuse. We have our bottoms-up compute reuse. And in the topic of compute reuse, there's this final piece, which is the computational control system. So we have a bottom curve here, which are the X264 presets that you're familiar with. Very fast, faster, fast. Different visual qualities on the y-axis, different computation required on the x-axis. On top of that is our system, which is the dotted curve. The dotted curve is 200 presets, 200 tool presets. And the key difference here, well, there's several key differences. One is the curve is higher, 15% visual gains. One is it's shifted to the left. It's half the computation required for each of those quality levels. The third is we dynamically change between these presets based on the measured load of the system. So you can just choose a static preset if that's what you want to do. But if you don't want to, you want to use all the compute available on the platform, you can let the system decide what preset should I be running at for this complexity of content and the number of channels that I have loaded on the chassis. And it's going to choose the optimal point to make sure that no cycles are ever wasted, and you're never going to break down. Your stream's never going to break down. You're never going to drop any frames because you don't have enough compute. The system's going to look after that. So another look at that, just specifically for X264 medium preset, that takes a specific computation, and it's going to deliver a specific visual quality. So 1 point on this graph. If you happen to move to the left of that point, if you have more computational power available than what that preset needs, there's going to be idle on your CPU that's not used, just wastage, right? If you move to the left of that point and you're doing live video, your video is going to break down. If you're not doing live video, it's going to run slower than you want, okay? If you use our curve, which runs on top of that, then it's going to dynamically adjust so that it's going to always be using all the compute available and never breaking down. Okay? Okay, so that's the topic of the deep ABR profile reuse. That's computational gains for ABR, specific to ABR. The second topic I wanted to cover more briefly, and I'll just do a time check here. Yeah, we're good. Is intelligent, fast, latency-free, per scene, immediate feedback resolution control. So this one is control gains specific to ABR encoding. So again, I'm going to start off with a bit of a complex block diagram and then move to a more simple example. But what we have on the left, we have our candidate resolution profiles going again into a content analyzer. Now this system overlaps with the encoder is the key here. So it's not a pre-process to the encoder. We're going to take a look at what is the ideal selected ladder profile for each output on the right to be outputting to achieve the best video quality for a per title type quality on the outputs. And we're going to do that in an overlapped fashion with the encoder itself so that you're incurring no additional latency. Also, it doesn't require really much compute because it's reusing the compute from the encoder itself. The key portion is actually this feedback line coming from the bottom right from the encoder itself, which the encoder state is informing the selection process of the ladder what the best output to use is, because it knows the encoder buffer state, and it knows the quality that the encoder is currently running at. So it can make the optimal choice based on look ahead for the next segment of what segment should it output to get the best quality. It doesn't have to guess. It's not a pattern recognition system, right? It's built into the encoder, integrated with it, not slapped onto it, so that it can make the optimal choice without incurring any latency and without incurring any significant additional compute. Okay, so that's the, and it runs live. So here's just an example on the FPGA product of 2 megabit live stream. And if you keep with the static output of the ladder and just use a 1080p 30 at that bit rate, you can see on the left the quality that you'll get. If you engage this dynamic resolution selection output selector, you'll see on the right the quality that you get, because it'll dynamically drop down on the segments where it needs to avoid the video quality loss. And it'll bump it back up again when it's not going to incur video quality loss. Okay? The key here is immediately adaptive. Okay, so just, that was a fairly quick run through, but again, I just throw up my first slide again in terms of what I covered today, and I have time for questions. Yeah.
Just for the slide before this one, when you say you adapt the resolution as you go, I'm sure you don't do it on a frame-per-frame basis, but you decide the point where you need to switch. And if someone is doing segment duration, how would you handle that? Are you going to have a variable segment length so that you need to change the resolution on a segment boundary for ABR application?
Yeah, that's correct. We changed the resolution on the segment boundary and signal that in the HLS so that the player is not surprised. Yeah.
Any other questions?
This is similar to other presentations we've seen before here, at Streaming Media West, where they've done the same type of approach in the output, but they've done it with massive compute and massive delay for VOD type applications, if you happen to attend the Apple session, right? So this is how to do it with the same deterministic quality, but with very little compute and no delay.
Okay, thank you. Sorry.
So did you say the plugin is available in FFmpeg with the algorithm implemented here?
Yeah, this is available as an FFmpeg plugin, both for the x86 solution and for the FPGA solution.
Are those only applicable to because your examples only show H.264. Does it apply to any other codecs?
So the methods that I was describing today could apply to any codecs. I was keeping it very generic, and any platform. So trying to show how you can get some good gains on whatever platform you're using or whatever codec you're using, whether it's current codecs or future codecs. Today, what we have available is ABC on both the FPGA and on the Xeon as an FFmpeg plugin.
Okay. And the latency improvement you have here, you have a matrix, like how much latency with this algorithm?
Yeah, this incurs no additional latency, assuming that you have these particular blocks in your encoder. So the latency in this block diagram is your look-ahead buffer for your rate control. So assuming that you're configuring your encoder with a look-ahead buffer, then you're already paying that latency for this system, because this system overlaps with your encoder. The statistics that it needs in the content analyzer, the encoder is also gathering. As I mentioned previously, the encoder is gathering information about how complex is the texture in the image, how complex is the motion in the image. That's already being gathered by the encoder. This look-ahead buffer that you fit your segments into, because as was the previous question, they was asking, when do you transition? You transition between segments. But to do that, if you want to do it optimally, you need your whole segment in your look-ahead buffer for optimality. But if your whole segment doesn't fit in the look-ahead buffer, that's okay. You'll be slightly suboptimal. You can run at a much lower latency, your overall encode. And you'll just make the decision based on the first portion of the segment. So it's still going to be pretty good, especially if your segments are aligned to scene boundaries, right? So it's going to be very good in that case. So this doesn't incur any additional latency, right? It's a latency-free system. Yeah.
Okay.
The latency is paid in the encoder itself already.
So along with the line, so the look-ahead buffer, is there any requirement on what the size it should be?
Yeah, if you want to get it to be optimal, like some of these brute force approaches that have been discussed, where you look at every potential option, for optimality, the look-ahead buffer should be your segment size. So say your segment size is 2 seconds, then your look-ahead buffer should be 2 seconds. But that's probably more than you want to pay, so you may run with a half-second look-ahead buffer. And because if your segments are aligned to scenes, then it's going to make the right decision for the scene based on the first 500 milliseconds of that scene that it sees. So it's probably an almost optimal decision, very close.
Hi. With both your FPGA and software solutions, could you explain the pros and cons of both? How do they fit together?
So these methods that I was talking about today, they're generic. And it doesn't matter whether you choose to go with hardware, you choose to go with software. Some people, for their applications, prefer hardware or software. That's not specific to our solution. That's more specific to the platform choice of the customer. So if the customer prefers hardware, we'll give them this on hardware. If the customer prefers software, we'll give them this on software. Both are available in the cloud. Both are available as on-premise options, either the Xilinx FPGA or the Xeon processors. So it's the customer's choice. Yeah.
From the beginning of the presentation, you were talking about the computational savings. I would like to ask how, and you said you can reach up to 50% savings by reusing everything across the ladder. How much compromise on compression efficiency? Do you have any numbers which could be a guidance here?
So that was the key of my title screen that I was trying to get across, is that we were improving the video quality, not compromising it when we do the reuse. So during the tops-down analysis, for example, we're gathering better quality information for the lower ladder rungs than what we would be able to do if we did it on the lower ladder rung itself, because encoders do things in a blockwise fashion, right? So if you're at a low resolution, you're only going to get one piece of information per block. But if you reuse it from the higher ladder rungs, you're going to get multiple pieces of information per block. So you can make a much better decision in that lower ladder rung as to what to do for your encoding. So you actually improve the video quality while saving compute. That's, we didn't want to, most people do start with the premise that they're going to compromise video quality to get compute savings, but that's not necessary. You don't have to make that presumption.
Is it consistently the case? Repeat the question, please.
Oh, sorry. Yeah. The question was, is it consistently the case? Well, yeah, nothing is ever absolutely consistent in video encoding. There's always variation. So statistically, there's always an average gain, and there's variation about that gain. And you really need to run more than one source if you want to verify it. You should run a large suite. Yeah.
Any other questions?
So when you're choosing the selected ladder profiles that are of the highest quality, you've got their video quality statistics. Can you explain which metrics you use and what drove that decision?
Sure. So what we have internal to our encoder is a quantization parameter, which is a rough idea of the video quality. On top of that quantization parameter, you have your visual models, which are like eye tracking models, models that say, for faces and skin tones, you should put more bits into those areas. For text and graphics, you should put more bits into those areas because they're things that people are looking at. Uncovered, covered areas in the video, when a car moves and the road is uncovered, that if you're not doing a good job of those, that can be really disturbing to the viewer. So those are all part of the visual model, which is a modulation factor on top of the QP, or the quantization parameter of the encoder. So these models are, if you just use, say, a metric like PSNR, which is maybe what you were referring to, or VMAF, then it's not going to have all of those models in it because it can't afford to, right? But an encoder is a much more complex beast. So a broadcast encoder has to have all those models in it to be competitive. So that's what we're using there for the video quality statistics. Yeah.
Okay, thank you very much.
Well, thank you.